Hello, I'm Jarrett Laddie, and this is the Physics 2212 Lab 1 charge tapes. The purpose of this lab is to estimate the charge on two different charge tapes by making an observation about their interactions with each other and with a positively charged pin. And once we find that charge, we need to determine how many excess charge carriers are on said tapes. And so some rough results are the tapes have the same charge. Both tapes are positively charged. The charge on the tape is roughly 1.26 times 10 to the negative 8th coulombs. The number of deficient electrons is 7.875 times 10 to the 10th. And the ratio of electrons to atoms is 1 electron per 4.838 times 10 to the 6th atoms. The three main physics concepts that are used in this lab are gravitational force, which on Earth is just Fg equals mass times gravity, which I'm using 9.81. Coulomb's law, which states that electric force is equal to the Coulomb constant times charge 1 times charge 2 over their distance squared, where I use 9 times 10 to the 9th for my Coulomb constant. And Newton's second law, which states that the sum of all your forces is equal to the mass of an object times its acceleration. And conversely, if an object is at rest, then the net force on that object must be 0. Next is the system that this experiment's taking place in, and a couple assumptions we're making just to make the experiment a little easier. So our system is the charge tapes, and for the one experiment where we determine the charge of the tapes, the charge pin that we bring in. And the surroundings are stuff like the neutral table and books that they don't really have any impact on what we're calculating. And a couple assumptions we're going to make are that the charge tapes can be treated like point charges with all the charges concentrated at the center, and we're going to assume that both tapes have an equal charge. Basic procedure for the experiment is as follows. You're going to apply a long strip of tape to a table to make a base tape, create two chargeable tapes by measuring out 20 centimeters of tape, folding over the end to make a handle. Then you're going to charge them by applying them to the base tape on the table and then ripping them off quickly. And then with your two charge tapes, you're going to observe a couple interactions. First, you're going to bring them close together to see if they attract or repel each other to determine how their signs are relative to each other. And then you're going to bring it near a plastic pen that you've either rubbed on your clothes or hair, giving it a negative charge to see how it interacts with that to determine the sign of the charge tapes. And then you're going to drape one of your charge tapes across two books so that it hangs down slightly due to the force of gravity. Bring your second tape closer and closer until the tape starts to float, meaning that the force of gravity has been overcome, so that's right about the point where your electric force is equal to your gravitational force. Observations that my group made while we were doing our lab is that the charge tapes repelled each other when they were brought together, so they must have like charges. The tape was attractive to the negatively charged pin, so the tapes must be positively charged. And our tape began to float over the other tape when it was about 2.7 centimeters away. So to determine all of our values, we first stated that Scotch tape has an approximate mass of 1 gram per meter. So our 20 centimeter piece of tape has a mass of 0.2 grams, which means that our force of gravity is equal to its mass times our constant. And we assume that as the tape floats, the vertical forces on the books, from the books on the tape is negligible. And since when it floats, it has a net acceleration of 0, we're going to set our force of gravity equal to our electric force and then isolate for Q, which gives us that Q is equal to the square root of our force of gravity times the distance between the two squared, all over our K constant, which gives us a value of 1.26 times 10 to the 8th coulombs. And the number of deficient electrons is just going to be our charge divided by the charge of a single electron, which gives us 7.875 times 10 to the 10th. A few more calculations. We found the number of atoms on the surface area of our tape by first multiplying the width of our tape times the length of our tape to get the surface area, and we were told that there are approximately 10 to the 20th atoms per square meter, so our surface area has about 3.181 times 10 to the 17th atom, and our ratio is just simply the number of deficient electrons we found earlier over this number of atoms we just found, which gives us our 1 electron per 4.838 times 10 to the 6th atoms. In my glow script representation, I just set out all of my fixed variables at the top, including the observed ones, such as the distance between the tapes when they began to float. I created my two forces, one for gravity and one for the electric force, both of which are equal in magnitude. Created two particles, one for our charged tapes. Then calculated Q using the same calculation that we did earlier, taking our electric force, multiplying it by the distance, dividing it by our K constant, and then taking the square root. And then we're printing out the number of charges, printing out the number of electrons on the tape using that same calculations, and then creating two vector representations of our forces on the particles. And there's not a ton of difference between this and the actual experiment, given that my code takes a lot of the observations from the experiment. So it's more of a free body representation rather than a prediction.